What's up, Chemistry Uncovered enthusiasts? This is episode number 3 of the Chemistry Uncovered YouTube series. I hope that wherever you guys are on this beautiful earth, on this earth full of hydrogen, nitrogen, carbon dioxide, full of the elements of the periodic table, I hope that this video finds you guys well and you guys can learn more about periodic tables, because again, the ultimate goal of this YouTube channel, of my Chemistry Uncovered's mission, is to make chemistry fun, collaborative, and educative. And this is a tutoring YouTube channel. So if you guys need help on chemistry, this is the perfect place to learn chemistry. Now, without further ado, let's get on to the content, right? We're talking about periodic table part 2. Last week we talked about, as a recap, what did we talk about last week, right? Last week, we talked about the Haber-Bosch process, which is the synthesis of ammonia. Basically, N2 plus H2 equals NH3. Ammonia is NH3. And the Haber-Bosch process essentially makes it easier for crops to grow with fertilizer, and, it helps speed up, the production of food, crops, and help advance society. And it's arguably one of the most important synthesis reactions on planet Earth. We also talked about the history of the periodic table. We talked about, Dmitry Mendeleev. Now, who is he? In 1869, he created the periodic table during the scientific revolution, and he organized it. He organized it in order to, group elements and to have a reference table for, the elements of the world. And then we also talked about the periodic table, which last week we talked about the elements of the periodic table, such as hydrogen, the example of hydrogen. We talked about periods and groups. And we also talked about metals, metalloids, and non-metals. And today we're going to go further about the periodic table and how it works, right? Like, what are the groups and what does it mean? Now, to start off, you might be asking, Chemistry Uncovered, what even are periods and groups? I didn't talk about this in the previous video, but periods is essentially the rows on a periodic table. So the rows goes horizontally. It determines the amount of energy levels. So as you go down a period, the amount of energy levels increases. So for the first row on a periodic table, the amount of energy levels is 1. Second row, amount of energy levels is 2. Now the columns, the vertical lines, the columns in a periodic table are they determine the amount of valence electrons in an element, right? So as you go right a group, there's more valence electrons, meaning that there's more electrons on the outer shell of the atomic structure, on the outer shell of the atom. And so for group 1, there's 1 valence electron, and for group 2, there's 2 valence electrons, right? And now, since they have the same valence electrons, that means that they have the same properties, and their reactivity is about the same. So to talk about valence electrons, as I said, as you go right a group, the valence electrons correspondingly increases. So for lithium, there's 1 valence electron. For lithium, that's Li's over here, there's 1 valence electron. And for phosphorus, since it's over here, group 5, there's 5 valence electrons, right? It's group 14, there's 5 valence electrons. For energy levels, as you go down periodic table, the amount of the energy level increases. So for sodium, since it's the third row, since it's the third period, the energy level says 3. And bromine, since it's the fourth period, the amount of energy levels is 4, right? To start off, alkali metals. For the exception of hydrogen, the other ones, lithium, sodium, potassium, rubidium, cesium, and francium, they all have 1 valence electron, right? And now, they all have the greatest atomic radii due to, effective nuclear charge. And we're going to talk about effective nuclear charge when we talk about periodic trends in the next video, so stay tuned. And they also have high reactivity and metallic character. High reactivity meaning that they can react well with other elements, with other atoms. Metallic character meaning that they have a sea of delocalized electrons, meaning that they're most likely to lose their 1 valence electron because it's the least attached to the nucleus. And we're going to talk about that later in this YouTube series. Alkaline earth metals. Alkaline earth metals is group 2 in the periodic table. Now you might be wondering why it's named alkaline. It's because these metals, they form alkaline solutions when reacted with water, and alkaline solutions are hydroxides. Hydroxides being OH minus. Okay, hydroxide and hydrogen plus are very important in acid-base reactions, and we're going to be talking about that later. And the properties for alkaline earth metals: high reactivity, as the alkali metals have, and also metallic character, because it's more likely for them to lose electrons to become the most stable, right? To go to the next one, transition metals. To transition to the next slide, transition metals. You get my joke. These are group 3 to 12. Valence electrons varies accordingly to the column it is. So for gold, since it's column 11, it has 11 valence electrons, and for iron, since it's column 8, has 8 valence electrons. It's named a transition metal because it has transitional behavior from S and P blocks, and we're going to be talking about the S and P blocks as part of quantum chemistry, and we're going to be talking about quantum chemistry later in this YouTube series. And also, these transition metals have they're good conductors of electricity due to the large sea of electrons, and also they have high densities because of that d orbital, that d subshell. It makes it more compact, right? And also it makes sense because silver, copper, iron, gold in the real world, they have high densities, right? Next one, post-transition metals, metalloids and non-metals. Post-transition metals are the highlighted red ones. Those are soft and brittle. Metalloids are the green outline ones: boron, silicon, germanium, arsenic, stuff like that. The metalloids, their properties are between metals and non-metals, so they're semiconductors of electricity. And then non-metals, they aren't good conductors of electricity, and they're very brittle. So that's that. And then halogens. Now halogens is my favorite group because it's super important in covalent and molecular bonds, and also Hofbrinkels, right? Now halogens is group 17, 7 valence electrons, because it's 7 valence. And then Hofbrinkel, meaning that it's a diatomic molecule. So all of these, for the exception of astatine, atomic number 85, all these fluorine, chlorine, bromine, iodine, they make bonds with themselves to have diatomic molecules. Di meaning 2, so 2 atomic molecules, right? Now these elements have high electronegativity because they're the most likely to attract an electron to become the most stable. And then finally, but not least, noble gases. Noble gases have 8 valence electrons to group 18. They're the rightmost column group on the periodic table, and they have the smallest atomic radius because of the effective nuclear charge that we're going to be talking about. And then they're the most stable because of the octet rule, and also because they have fully filled shells and it's all in place. And so since they're the most stable, they're non-reactive. And then also lanthanides and actinides, we're not really going to talk about this a lot because they're not really used in chemistry a lot. But they are essentially the F subshell, meaning that F subshell, again, quantum chemistry, the F subshell can hold 14 electrons, and as you can see, there's 14 groups here, meaning that they can hold 14 electrons, 14 valence electrons. And so the top period is lanthanides, and the bottom period is actinides, right? And all of these slides, the source is none other than the GOAT, Chemistry Uncovered. So if you want to, use these slides as the source for, studying for tests or presentation, you can always feel free to use these slides. This is a platform where not only I tutor chemistry, but I want to make a collaborative environment to make the world a better place. And that's my end mission. Why do we learn periodic table? Why do we learn the Haber-Bosch process? Why do we learn what groups are? It's to help us understand the world, help us making, dye and, stuff like that, and help us develop drugs to make the world a better place and make mankind a better place to live. So thank you so much for watching, and Chemistry Uncovered is consistently trying to push out state-of-the-art content, and we are going to have interviews, labs. We're going to have, Chemistry Uncovered is always thinking about new ideas for this YouTube channel, and stay tuned because this YouTube channel is only getting started. So thank you, and please subscribe because 60% of you guys still aren't subscribed. So please subscribe. Thank you so much. Have a good day. Peace out.